If you own a portable digital music player or a smartphone, you are likely one of the millions of people who benefit from nanotechnology. Nanotechnology has allowed us to advance electronics to pack gigabytes of music and media in the palm of your hands. But this is just the beginning. Imagine in the future computer chips the size of a quarter running at truly phenomenal speeds, enhancing multitasking work productivity and delivering unparalleled photorealistic media. Nanotechnology refers to the research of creating and using materials at the length scale of 1 to 100 nanometers. A nanometer is 1/billionth of a meter. Research at this scale manipulates and controls individual molecules, or even atoms. Carbon nanotubes, commonly known as CNTs, are carbon atoms arranged in a tube geometry. They are of particular interest to electrical engineers because nanotube circuits can conduct electricity ballistically, meaning there is minimal resistance. In addition, the intrinsically small size of carbon nanotubes may allow much smaller circuits than today's silicon circuits, further improving speed and computational power. Here, within Stanford University, is one of the many nanofabrication facilities funded by the National Science Foundation. This is where our journey begins, as we follow the life story of carbon nanotubes, from synthesis and growth to device and circuit fabrication, all on a wafer scale. CNTs can be grown on quartz, the same material found at the heart of most wristwatches. The process first involves a long quartz anneal, which essentially bakes the quartz wafers for 17 hours in a furnace at 900 degrees Celsius. This step is crucial as it repairs the quartz surface, allowing us to obtain straighter carbon nanotubes during growth. On each quartz wafer, catalyst nanoparticles, which facilitate CNT formation, are placed in a stripe pattern. Finally, the quartz sample is ready for CNT growth in the growth lab just down the hall.
We have fine-tuned our CNT growth conditions so as to optimize density, length, and uniformity. After much research and engineering, we've arrived at an optimal temperature of about 860 degrees C and a subatmospheric pressure of about 300 torr.
This method gives yield to straight, long, dense, and uniform carbon nanotubes, all on a wafer scale. Why are straight CNTs so important? Imagine some faulty wiring in your house. That could lead to your ceiling lights not being controlled by the correct switches. Similarly, CNTs that are misaligned would create incorrectly wired circuits. High density is also important as it has a direct impact on the performance by increasing current, just like how multiple lanes on a highway allow more cars to reach their destinations. What we have achieved here are carbon nanotubes compatible with very large-scale integration. What that means is that the process is repeatable, robust, and most importantly, scalable for practical commercial applications. While the CNTs in this lab are grown on quartz, the Stanford team developed a carbon nanotube transfer process, which will then allow the tubes to be further processed on any type of wafer.
What we intend to do is to evaporate 100 nanometers of gold on top of the CNTs, such that the nanotubes are embedded in gold. This gold acts as a temporary transfer layer. In this electron beam evaporator, this is where we load the wafers, and this is where we load the gold. After the gold is heated, melted, and evaporated, the wafers come out covered in a 100 nanometer gold film.
After gold is evaporated, we apply a special tape. The tape peels the gold away from the substrate, and the CNTs are also peeled off along with the gold. The tubes are then applied to the new substrate. The tape is special in that when it is heated to 120 degrees Celsius, it loses its stickiness and can be removed while leaving the CNTs unharmed. The gold is then chemically dissolved away. With the CNT material in place on a new substrate, we use standard lithography techniques to create the electronic devices. In the lithography process, photoresist is first spun onto the wafers. Then, an exposure tool, such as this ASML stepper, is used to literally imprint the desired pattern onto the resist. Next, the photoresist is developed to create the pattern. The overall process is very much like the exposure and develop process used for traditional camera film. Lastly, after metal is evaporated onto the wafer, we do liftoff, and the metal only stays in the pattern we previously defined. Half of the improvements in today's chips that allow for better processing speeds and lower power dissipation can be attributed to some form of device innovation. The choice of structure, geometry, and even metals can all affect the device performance and properties. To fully take advantage of CNTs, we need to optimize and experiment with all of these to find the very best. In the next step, the design process involves formulating design methodologies that stem from the analysis of optimal trade-offs. Jerry Zhang and Professor Mitra are experts in robust systems, and will talk a bit about robust CNT circuits.
It is very difficult to guarantee perfect alignment and positioning of all carbon nanotubes. Now that creates a huge problem when you're trying to design logic gates out of carbon nanotubes.
Yes. Consider a large computer chip that consists of 1 billion transistors. We need to make sure that each and every of the logic gates work properly. Now, this can get really challenging if we have a large number of misaligned carbon nanotubes.
That's why we are working on robust design principles that guarantee that we have correct logic functionality in the presence of a large number of misaligned and mispositioned carbon nanotubes. And that's where the magic is.
So combining all of the above techniques, from CNT growth to robust circuits, we have successfully demonstrated carbon nanotube logic gates, which are the fundamental building blocks of computers. By putting together myriads of logic gates, circuits are formed. And by combining numerous circuits, systems are formed. Finally, with a little bit more design, these systems might one day become the products you hold in your pockets. Isn't that right, Professor Wang?
That's right. What you're seeing today is state-of-the-art technology in carbon nanotube electronics. What we are doing here is to turn fundamental discovery in science, such as carbon nanotubes, into useful technology. But it would take a lot of hard work and teamwork to make it all happen. Please come join us.
Yay!